Hello, I am Salma Kazeminia from Helmholtz Munich, and I would like to introduce anomaly-aware multiple instance learning for classification of rare anemia disorders. I would like to start with a simple question to illustrate what happens in a multiple instance learning-based classifier. Here you see 4 sets of emojis. In the first one, all instances are smiling emojis, while in other sets we can see other kinds of emojis as well. In a multiple instance learning definition, we call the first set a negative set and others are positive sets. The question here is in which set you see runny nose symptom, and the answer is the third one, because of the existence of these 2 emojis. I think you agree that answering this question would be easier if we could see these sets like this. Making such a hint for a multiple instance learning-based classifier is the main idea of our work. In other words, we learn common instances and decrease their visibility, which is equivalent with highlighting uncommon instances. Then, finding a match between the query and input would be an easy task. Note that for the first step, we have a bonus. In negative sets, we have enough common instances to learn their features. In anemia disorder diagnosis, instead of sets, we have microscopic images of blood samples, and cells are instances. Each sample contains a high number of normal cells, and if it belongs to an anemia case, it contains a low ratio of abnormal cells as well. Close monitoring of blood samples in rare anemia patients is crucial for diagnosis, prognosis, and disease severity estimation. However, identifying the low ratio of anemia-relevant cells is a needle in the haystack search and needs to be assisted by automated tools. Similar to the previous illustration, rare anemia diagnosis is a multiple instance learning problem since we only have sample-level annotations. However, MIL is a data-hungry method and we have a limited access to data due to a scarcity of this kind of disease. That's why we propose the anomaly detection idea to make the problem easier for the MIL classifier to solve. Okay, now we know what is the idea and where is the application. So let's take a look at the training procedure of our method. For training, we consider 2 steps. In the first step, we only feed blood samples of healthy cases to learn what a normal cell is. Then, in the second step, all the training data, regardless to their label, are used to learn the classifier. In the architecture of our method, we embed a pre-trained object detector to detect cells. Then, each cell in a sample is mapped to a data point in the latent space using a deep encoder. After passing all cells of healthy cases, we will have a distribution of latent data points, which can be estimated by fitting a Gaussian mixture model on it. Here, we save properties of the estimated distribution for the next training step. In each iteration of the second training step, an image set is randomly chosen and its cells get mapped to the latent space. By measuring the distance of each cell to the saved healthy distribution, we assign an anomaly score to it, which gets combined with the attention score and results to a pooling weight to specify the contribution of each cell in the final classification result. We evaluated our method in classifying 4 types of rare anemias. Our experiments showed that anomaly-aware multiple instance learning outperforms other methods in this application, containing state-of-the-art, which only embeds attention mechanism in the multiple instance learning classifier. Moreover, this method is explainable in the cell level by introducing an anomaly degree for each cell. In this way, medical experts can check if abnormal cells are detected correctly and if their features are matched with the final classification result. In summary, our method is a simple solution for multiple instance learning training by using only a limited amount of data. To achieve this, we estimate the distribution of normal cells in the latent space and highlight abnormal cells to contribute in the final classification. Fitting a Gaussian mixture model is a simple data-efficient method to estimate the distribution of normal instances. However, its performance is limited to the complexity of normal instances definition. For example, in leukemia classification, GMM cannot cover all diverse healthy types of white blood cells. In this way, saving the main idea of anomaly-aware multiple instance learning, we can apply other out-of-distribution detection methods, considering our access to the training data. Thanks a lot for your attention.